Okay, chapter 4. Chapter 4 talk about exponential and natural logarithm functions. We've talked about exponential functions earlier. So the standard form is like this. Well, a lot of times we have a coefficient, right? We have a multiplied, a scalar, multiplied by b raised by x. So exponential functions. So we have this called the initial term. Let's give some example. F of x equals to 2 raised by x. You see x appears in the exponent. So that's why it's called an exponential function. Or maybe we have function as 2 raised by negative x. Remember 2 raised by negative 1, so this can be thought as 2 raised by negative 1, then raised by x. So that's a 1/2 raised by x. Or just 1 over 2 raised by x. Because 1 raised by x will still be 1. And this one we call doubling model. Right? So as x increased by 1, the function value doubles. Think about x equals 0. If x is 0, we get a 1. Right? 2 raised by 0 will be 1. If x is 1, then we'll get a 2. X is 2, we get a 4. X is 3, we get an 8. So on and so forth. You see, every time the function value doubles. 2 doubles 1, 4 doubles 2, 8 doubles 4, so on and so forth. That's why it's called a doubling model. And this one is called a halving model. If x is 0, we get a 1. 2 raised by negative 0, still 1. If x is 1, we get a half. If x equals 2, we get a 1/4. X equals 3, we get a 1/8. See, half is half of 1. 1/4 is half of a half. 1/8 is half of 1/4. So that's why it's called a halving model. So those are two famous exponential models. So this is a doubling model. Right? If we graph it, the graph looks like this. And this would be when x equals 0, right? Y value is 1. Then this to the left-hand side will never touch x-axis because x-axis also is y, the function value equals 0. But the function value will never be 0. So this will never be 0 because 2 raised by anything will never be 0. And 2 when x increases, right, this goes to past infinity, the function value. If we plug in negative value, f of -1, then it goes this way. You can imagine this is -1, then we get a half, -2, get a quarter, so on and so forth. So the laws of exponents, let's see these examples. So here we have 4 raised by 5x divided by 2. So this is saying we have 4 raised by 5x divided by 2. We can rewrite this as 2 because 4 is 2 squared. So 2 raised by 2 raised by 5x divided by 2. Then when we have 2 layers of exponents, we multiply them. So 2 raised by 2 multiplied by 5x divided by 2. Well, 2 times half, these two cancel to be 1. So that's 2 raised by 5x. Then we have to write this down as 2 raised by kx. So in this case, k equals to 5. Let's see the second one. Inside, we have two terms. We have 2 raised by 4x, and then 2 raised by negative x. So this is multiplication. So if the multiplication of the same base, we can add their exponents plus negative x, then raised by half. Well, 4x plus negative x, that's 4x minus x. So that's 2 raised by 3x, then raised by half. 2 layers of exponents, we multiply. So we get a 3x times half, that's 3x divided by 2. So we can write as 2 raised by 3 over 2x. In this case, k equals to 3/2. Let's see C. A raised by x divided by 3, we can think, because we have different base, right? We have A, we have 16. But what do they have in common is 8 can be written as 2 raised by 3. 16 can be written as 2 raised by 4. So 2 raised by 3, that's 8. Then raised by x divided by 3. Multiply by 16, which is 2 raised by 4. Then raised by 3x divided by 4. Now we see when we multiply, we have 2 layers of exponents. We multiply 3 and 1/3 becomes 1. So 2 raised by x. Then this one, 4 times 1/4, that becomes 1. So that's a 2 raised by 3x. Then we add those two together. So we get 2 raised by 4x. Right? Because x is just 1x. 1x plus 3x is 4x. So in this case, k equals to 4. Lastly, we have this division. So for 10 raised by x, we can write as, well, first, both raised by x, we can write like this, 10 divided by 5. Then raised by x, right? Because 10 raised by x, 5 also raised by x. Then what's 10 divided by 5? 2. That's 2 raised by x. So what is the number before x? That's 1. So in this case, k equals to 1. Okay, so this is a graph of 2 raised by x. So we can make a table. We give x some value, x negative 3. Then we have 1/8. Right? 1/8 is 0.125. X equals negative 2, we get a quarter, which is 0.25. X equals negative 1, we get a half, which is 0.5. X equals 0, we get a 1. 1, we get a 2. 2 squared is 4. 3, 2 raised by 3 is 8. So we see the graph, make these points. So that's the graph, exponential growth, right? When x increases, function value also increases. So it's an increasing function. So we call this exponential growth. If the base is 3, function raised by 3 raised by x, you see the graph becomes sharper. The increase is faster. Now we have this purple color. So this purple color is a halving model. So half raised by x or 0.5 raised by x. So we see this function decrease in function, right? As x increases, the function value decreases. Let's see this one. This one is saying solve equation, right, with exponentials. So let's see, we are given this function, right? And we want to determine x value for the function value to be 27, which means 27 equals 3 raised by 5x. And 27 we can write as 3 raised by 3. Now, since the two base are both 3, so the exponents has to be equal. So 3 has to equal to 5x. Then solve for x, we divide by 5 on both sides. So x equals 3 over 5. Okay, so that's just, introducing exponential functions. And it's very similar for exponential decay. Exponential growth, it's an increasing function. Exponential decay, decreasing function. Like doubling model and halving model, that's just opposite, the inverse. They are not inverse, right? That's just opposite. They're symmetric with the y-axis. Okay, now we're going to talk about something called a natural Euler number. Exponential function with a base to be Euler number. Euler number is about 2.71828 . It's just like a pi. Pi equals 3.14 . Irrational number. So whenever we see E, we think that that's about 2.72. All right, you can just give a rough approximation in our head. Now we like to talk about the E raised by x. All right, so like this. E raised by x, the function, exponential function. This is talking about we use the difference quotient to find the value. Oh, okay. So we need to learn this formula. So when we differentiate exponential functions, so what do? We have this m. And what's special about this? You see the exponential function always appears in its derivative. We differentiate 2 raised by x, we still get 2 raised by x. The difference is just this scalar m. This is scalar m. Yeah, it's some number. What is this number? This number is log base 2. Right. So this is written as m equals differentiate 2 raised by x at x equals 0. So finding this value, m value, that's about 0.693. But we want to use exact number. We don't want to use this approximation. So log 2. Let me see if I can find it. Okay, so this textbook didn't write about that. So let's do this. So in general, so this m is kind of ambiguous from here, right? So what do we understand? We understand as log, if you have a calculator, because I'm gonna bring my calculator to check the values. We just have to carry on log base 10 of 2. Log, sorry, I can't find my calculator right away. Where's my calculator? Right here. Let me see if I have it. Usually on your calculator, you see log base 10. Okay. Log base 10. So log base 10 of 2 Then ln, so I talked about this a little bit earlier when we talk about logarithmic. Or maybe now I understand the textbook. The textbook want to talk about later because right now we're in exponential functions. Okay, let me not get ahead of this textbook. Let's just follow the textbook for now. So for now, just for us to remember, when we differentiate an exponential function, the derivatives still have the exponential function, but it just differ by this scalar m. Okay, just differ by the scalar m. If the base is 2, the scalar is 0.693. So next section maybe, we'll know exactly what this is when we talk about the logarithmic. Right? So this is scalar of this function. So usually when we talk about standard form of exponential functions, we write this way. We write f of x equals to a, some number, multiplied by b, some base, raised by x. So this is one we call initial value. What do we mean by that? That means when x equals 0. Right? When x equals 0, b raised by x equals 1. So 1 times a, just a. So that's f of 0 equals to 8. And we call initial value, so 0, 8. So in this case, we can think that way, right? So this m, just a scalar, it scales, which means it makes the 2 raised by x smaller or bigger. Right? If m is 2, it make a 2 raised by x twice as big. If m is half, it make a 2 raised by x half smaller. Let's see these two examples. So we want to calculate it. So for now, when we deal with 2 raised by x, we use the m to be approximately 0.693. We use this such value. Right? So we just get 2 raised by 3. We want to evaluate when x equals 3. We just evaluate. Right? We get a 5.544. If x equals -1, we have 2 raised by -1, which is half, then multiply by this number with 0.3465. So this is a similar idea, right? So when it's e, we have this. So when we differentiate e to the x, we evaluate at x equals to 0, we get 1. So you can think when we differentiate e raised by x, that's the m value. So initial value. So which means when we differentiate e raised by x, we just get itself because there's 1 times e to the x. So it's just e to the x, just itself. So there's something special about this e. That's here, right? When we differentiate e to the x, we just get e to the x. So that's the graph of e to the x. Because it's 2.7 something, so it's a number between 3 and 2, but it's closer to 3. So the graph is in between 3 raised by x and 2 raised by x. Okay, let's see this practice. So given this expression, we want to write it in this form. Okay. We want to write the initial value a, capital letter A, and e raised by kx. Okay, we want to find the k and a. So let's say this. So remember, we have, when this exponent is outside, we have to distribute this exponent to every one inside the parentheses. So we got a 3 raised by 2, because 1 times 2. Then e raised by 2x times 2, that becomes e raised by 4x. Then times e raised by x. Then divided by e raised by negative 2x. 3 raised by 2, that's 9. Then e raised by 4x times e raised by x, that's e raised by 4x plus 1x, that's e raised by 5x. Now, this is e raised by negative, we can rewrite as e raised by positive 2x. But remember, if we have 1 over e, that's e raised by negative 1. If we have 1 over e raised by negative 1, that's 1 over e. What's 1 over e? That's 1 divided by 1 over e. That's 1 times e raised divided by 1. That's just e. So if we have 1 over e to the 2, or we have e raised by negative 2, that's 1 over e to the 2. Or if we have 1 over e raised by negative 2, that's e raised by negative 2 becomes positive 2. So in this case, we have e raised by negative 2x in the denominator. So that becomes e raised by negative 2x, so which is positive 2x. Now 5x plus 2x, that's 7x. So we got 9 times e raised by 7x. So in this case, a equals to 9 and k equals to 7. Well, let's see b. B, everything raised by half, right? Remember, square root means half. So let's do the inside first. Inside, I have e raised by x times e raised by negative 7x, right? Because e raised by 7x in the denominator, I can write it as e raised by negative 7x in the numerator. That becomes e raised by x plus negative, that becomes minus. So that's the square root of e raised by negative 6x. Now I can write as e raised by negative 6x raised by half. So I multiply those two layers of exponents, negative e raised by negative 6x, multiplied by half. Well, negative 6 times half, which is negative 6 divided by 2, which is e raised by negative 3x. So in this case, a equals to 1, right? Because there's no number in front of e, which is 1. And k is negative 3. Let's see this example. So we want to find the tangent line to this graph. Well, remember e raised by x, the graph looks like this, exponential function. And we want to find when x equals 1, right, what is its tangent line? So what do we need to do? Remember, we need to find a derivative, right? Derivative of e to the x is just e to the x itself. But when x equals 1, this is just e raised by 1, which is e, at 2.718 something. So that's the slope of the tangent line. Then remember, when x equals 1, we can find f of 1, the function value, which is e raised by 1, which is the e. So we have this point, 1 comma e. Then use the slope intercept formula. Remember, y minus y1 equals the slope times x minus x1. Well, we can use this as x1, y1. So I have y minus e equals to, well, slope is also e, just a coincidence. They happen to be the same. X minus x1, which is 1. We simplify this, so y equals to e times x. Well, e is not a variable. E is just like a pi, a constant. Then minus e. Now, e times negative 1, that's minus e. Now we move this negative e to the other side, become positive. Negative e, positive e becomes 0. So the tangent line at x equals to 1, which is y equals to e to the x. Let's see this example. And we want to differentiate this and this one. So what do we do? First, we see product, right? We see this the function, maybe let's call this function g of x. Maybe call this f of x. So e to the x is f of x. 1 plus x squared g of x. Then we see g prime of x is a 2x. And the f prime of x is still e to the x. Then we use the product rule. Remember product rule? We take a derivative of first term, which is 2x, multiply by the second one, which is e raised by x, then plus derivative of the second one, which is still e to the x, then multiply by the first one, 1 plus x squared. That's it. That's the derivative of this function. Right? We see a product. We see 1 plus x squared as one function, multiplied by e raised by x is another function. So we need to use the product rule. Product rule is the sum, taking derivative of the first one, multiplied by the second one, taking derivative of the second one, multiplied by the first one. But the second one is a quotient rule, right? Quotient rule, remember, I don't like to talk about quotient rule. So I like to, first, we want to leave this half alone. So we want to write this as a half of 1 plus e raised by x multiplied by x raised by -1, right? Because 1 over 2x, that's a half of 1 over x. That's half of x raised by -1. And we don't want to carry this scalar into differentiations. We want to leave it outside. So we still have a half. We want to use product rule or quotient rule if you prefer. We take derivative of the first one. Derivative of 1 is 0. Derivative of 1, derivative of e to the x is still e to the x. Multiply by the second one, still divided by x. Then derivative of the second one, remember, is 1 over x squared. Plus negative become minus. Right? Then multiply by the first one, which is 1 plus e to the x. Yeah, so half of this. So that's it. So we leave the scalar outside. We just want to differentiate these two terms. We differentiate the first function, e to the x, 1 plus e to the x. Differentiate 1, 0. Differentiate e to the x is itself. Then multiply by the second one, so we have e to the x divided by x. Then we differentiate x raised by -1. Remember, x raised by -1 is a negative 1 over x squared, because minus 1 is -2. Then multiply by 1 plus x e to the x. So that's it, we can just leave like this. If you want to use quotient rule, in the end, you probably get this x squared. So you multiply x here, this one, get this one, x squared. Then the answer should be 1 over 2 of x e to the x minus 1 minus e to the x divided by x squared. Or even you can write this half here, 2x squared, right? Let's see this one. So given this one, we want to find derivative of y equals a negative x. Y to the negative x. We're going to do the same thing, right? So let's say function equals to e to the negative x. So when we take a derivative of this, we get first, we can write this as e raised by x, then raised by -1. Then e to the x is just itself, right? But then we have this -1 here. So in the end, we just get a negative e raised by negative x, right? We can see from here. So first, we just follow the rule. When the function raised by -1, we have -1, and the function raised by -2. In this case, it's e raised by x raised by -2. Then we differentiate e raised by x. Well, e raised by x just derivative just itself. Then e raised by negative 2x plus x, that's just e raised by negative x. So we don't have to do this a second time. So for us, we could just remember derivative of e to the x. I don't really need to write down as a function. Just remember e to the x derivative is itself. E to the negative x derivative is a negative of itself. Right? So this is to graph it. You see the symmetric with the y-axis of the positive e to the x. The positive e to the x, something like this. So this will be e to the positive x, exponential growth, increasing function. E raised by negative x, decreasing function. It's similar to 2 raised by x and 2 raised by negative x. Okay, this is doubling model, this is a halving model. If the exponent has a scalar, let's see, this is e raised by 1x, this is e raised by 2x, this is e raised by 1/3 of x. Okay. There's a scalar in front of this x. If the scalar is greater than 1, we see the graph, the increasing function increases more sharply. Similarly for the decreasing function as well. Okay. Let's see how do we. So more complicated exponential functions. The first one could be e raised by gx instead of e raised by x, e raised by g of x. So it's a composition of functions. So what do? If the we differentiate e raised by g of x, first we get itself always. So derivative of e term, always we get itself. Then we multiply g prime of x. Let's give an example to see. We have e raised by 3x squared. So g of x is 3x squared. So what do? First, we get e raised by 3x squared itself. Then the m, like remember, it's always m multiplied by the original function. Well, how do we find the m? M in this case is the derivative of 3x squared, which is 6x. Let's see these examples. So then in this case, y prime equals to e to the 5x itself, then derivative of 5x, which is 5 multiplied by 5. So first we have the function itself, e raised by x squared minus 1. Then we take a derivative of the exponent, which is 2x. So y prime in this case, so x minus 1 divided by x. So first we have the function itself, e raised by x minus 1 divided by x. Then we have to have derivative of the exponents. So how do we take derivative of this? X divided by x is 1 minus 1 over x. That's 1 minus x raised by negative 1. When we take a derivative, this becomes 0. This becomes minus, become plus, become positive. Minus times this minus become positive. Then x raised by negative 1 minus 1, which is minus 2. Which is, so differentiate that, we get 1 over x squared. So that's 1 over x squared. Or we can write it as e raised by x minus 1 divided by x divided by x squared. Right. So this is like a chain rule, right? Because this is compositional functions, so still apply chain rule. Let's see this example. So when we differentiate a function, we can always pull the scalar out. You see this 3 is a scalar. I can always leave it out. So I can do e to the 2x times 1 plus x squared raised by -1. I just rewrite it as a product, so I can apply product rule. I leave the 3 outside of the differentiation. So product rule saying taking derivative of the first one, which I get a 2 e to the 2x, right? Because the derivative of e to the 2x, first I have to have e to the 2x, then I differentiate the exponents, which is 2. Then multiply by the second one, which is 1 plus x squared. Then take a derivative of the second one, right? Which is 1 plus x squared raised by -2. Then I put in the denominator. Remember, always remember this. Derivative of this is just 1 over x squared, -1 over x squared, right? So in this case, plus minus. That's why this become minus. Then I have to multiply by the first term with e to the 2x. And also I have to multiply by the derivative of inside, right? What's the derivative of inside? 2x. And that's it. Right. So I write as a product. I write this function. I leave the scalar outside 3. Then I write the expression, rational expression as a product by doing the denominator to raise by -1. Then I use product rule. The product rule tells me differentiate the first term, first function, multiply by the second one, then differentiate the second one, multiply by the first one. Or you can use quotient rule. You can use quotient rule. In the end, it should be the same answer. But why these two answers look differently? Because in this case, we don't have a square term. If I want to square this term, I can multiply 1 plus x squared in the numerator. Now I can combine the numerators. The numerators, you see 2e to the 2x times 1. That's the 2e to the 2x. Then 2e to 2x times x squared minus 2x e raised by 2x. We see e raised by the 2x is the common factor, actually 2. We see this 2, this one, 2, this one is a common factor, so we can factor out. 2 times e raised by 2x times 3, that's a 6 e raised by 2x. Then multiply by a fraction. The denominator is 1 plus x squared. The numerator we have 1 plus x squared, 1 plus x squared minus x. Usually we want to write this in order. We write x squared first, then minus x plus 1. Let's see this example. Combine the returns from 2 investments. The investor puts 25,000 in 2 separate stocks, A and B. Invested 15,000 in A and 10,000 in B. The value of the account in thousands of dollars T years from its inception is given by this, such function. So f of t equals 15 times e raised by 0.02t plus 10 times e raised by negative 0.06t. So let's see the question. The question is asking, what is the value of the account after 4 years? Right? Which variable represents 4 years? T. This means t equals 4. This means t equals to 12. At what rate is a current change derivative? Right? This is talking about finding f of 12. But this is talking about rate of change. What is f prime of 4? F prime of 12. So let me just follow the textbook so I can skip some calculations. So F4, just plug in 4 for X. After calculation, we get about $24,000. After 12 years, about $23,000. But for B, it's talking about the rate of change, so derivative. So when we take a derivative, the function will get a 0.3 e raised by 0.02t minus 0.6 times e raised by negative 0.06t. After 4 years, we just plug in 4 for t. We get a negative 0.146 something. After 12 years, we get a positive 0.089 something. Okay, so I'm going to stop here for these 3 sections, talking about exponential functions, especially use this Euler number E.